chemical reactions. So it means it's symbolically representing what's happening in a chemical reaction. It tells us the number of atoms or moles of substances and how they rearrange. We use coefficients in our chemical reactions to show how many of each molecule, atom, particle we have. The atoms don't get created or destroyed. The atoms just get rearranged and the total number remains constant. Conservation of matter. Alright, let's practice balancing some reactions. When we balance some equations, we save the elements for last if possible, just because we can add as many of them as we want. We don't have to worry about balancing two things at once. We can just do one at a time. So for our first reaction, we've got ammonium dichromate going to chromium oxide, nitrogen, and water. Start with chromium. We have 2 chromium on the left, 2 chromium on the right. Those are balanced. Looks like we're going to go with nitrogen next. We have 2 on the left, we have 2 on the right, so the nitrogen's balanced. So we're 2 for 2. We've got 2 more elements to go. On the left we have 8 hydrogens. So if we put a 4 in front of the water, now we have 8 hydrogens on the right. Count up our oxygens. 4 plus 3 is 7, so oxygens are balanced. Combustion reaction. Start with carbon. 3 carbons on the left, so that gives us 3 carbon dioxides on the right. 8 hydrogens on the left gives us 4 waters on the right. 4 plus 3 is 10, so that gives us 5 O2s on the left. For our last reaction, we have ammonia plus oxygen. This is nitrous oxide and water. Start with ammonia. We want an even number of hydrogens, so that gives us 6 hydrogens. We'll make the number of hydrogens on the left even, so we'll put a 2 in front of ammonia. That gives us 6 hydrogens. Gives us 2 nitrogens, so we need to have 2 NO2 on the right. We will now have 3 waters, so we have 6 hydrogens on each side. So we have 3 plus 2 is 5 oxygens on the right. That gives us 2.5. What's that? On the left. Can't have fractions, at least at this stage, so we're going to multiply everything by 2. So we get 4 ammonia, 5 oxygen, 4 NO, and 6 waters. Stoichiometry is using those balanced equations then to figure out how much of a product we're going to get or how much of another reactant we need. So it's using math with balanced equations. Starting with the combustion reaction of methane, how much oxygen do we need for 500 grams of methane? First thing we're going to do is convert our methane to moles. So 500 grams of methane divided by the formula mass of methane gives us the moles of methane. Then we're going to look at the mole ratio between what we want and what we have. 2 oxygens what we want, 1 methane's what we have. Gives us 62.31 moles of oxygen that we need. So we convert to grams of oxygen by taking moles times formula mass of oxygen. We get 1994 grams of oxygen. Limiting reactants is when we have 2 quantities and we're trying to figure out which one's going to control the amount of product we actually get. Same reaction. Now we have starting amounts of both methane and oxygen. Which one's going to determine how much product we get? Same deal. We find the number of moles of each reactant by dividing by each's formula mass. We get about the same number of moles of each. That's no help. So we get 15.58 moles of methane, 15.63 moles of oxygen is what we start with. What we want to find out is how many moles of carbon dioxide will each of these produce. So we find the moles, do the mole-to-mole ratio. We find that we get 15.58 moles of carbon dioxide. It's a 1-to-1 mole ratio. 1-to-2 mole ratio for carbon dioxide to oxygen, so we only get 7.82 moles of carbon dioxide. That oxygen is our limiting reactant. If we want to find out grams of oxygen, take it or carbon dioxide, we take it times the formula mass. Theoretical yield compares what we get experimentally to what we should get based on thermodynamics. So we take the actual mass, divide by the formula mass. We take the theoretical yield that we calculated, 343.9 grams, and divide that into our experimental mass, 322.6 grams, and that will give us our percent yield. So we end up with 0.938 or 93.8% of what we should get theoretically, which is pretty good yield. And that is the rest of Chapter 3 for stoichiometry and chemical reactions.